Hello students, in previous class we already discussed about what is refraction, what is Snell's law and what is the principle of reversibility and how a medium can be determined as a denser medium or rarer medium depending upon the refractive index. And what is refractive index? So refractive index is the ratio of speed of light in free space with that of the speed of light in the given medium. Clear? So today we are going to discuss about how refraction takes place through a glass slab. Okay, so first of all we are going to discuss about the refraction through a glass slab. So how light gets refracted through a glass slab? So let's consider first a glass slab here. Okay, so let the name of the glass slab be X, Y and X dash, Y dash. Let the thickness of the glass slab be T. Okay, and here is a medium surrounding the glass slab, that is air medium, let it having refractive index mu A, and the refractive index of the glass slab let be mu G. Similarly, the lower surface X dash Y dash is also surrounded by the same air medium, so it's a refractive index mu A. So let's consider a light which is incident on the first interface, that is XY. Let this is be the incident light which is incident on the first interface XY. Let this is be normal N1 and the angle of incidence at this normal N1 be I. Clear? So now for the first interface XY, the light is travelling from air medium to glass medium. That means as air is more denser in comparison to glass medium, the refractive index of air medium, the refractive index of air medium mu A is less than that of glass, because air have refractive index nearly equal to 1, which is less than the refractive index of glass medium, that is 1.5. So here for the first interface XY, the light ray, let the name of the light ray be P Q. Okay, so the incident ray PQ is traveling from rarer medium to denser medium. So after it's entered through the denser medium by refraction at XY interface, it bend towards what? The normal, because in denser medium after refraction the incident ray bend towards normal, so it will travel like this. Clear? So again at the second interface X dash Y dash, which separate the glass medium with respect to the air medium. So let's draw a normal here. Let that is N2. So at N2, if this angle is known as refractive angle R1, so similarly this will be the same angle R1. So here the R1, which one is refracted angle at the interface XY, will be the incident angle at the interface X dash Y dash. And now for this ray QR, which is incident at normal N2 and goes through refraction by the interface X dash Y dash, which is separating the medium glass and air. For this incident ray QR, the incident ray is now traveling from denser medium to rarer medium, because glass is denser medium and air is rarer medium. That's why it will bend away from the normal. So it will move like this, and this angle will be known as the emergent angle or E. Clear? So first the incident ray PQ is traveling from air medium to glass medium for the interface XY, which will separate the medium air and glass, for which the light ray PQ travels from rarer to denser. That's why it bend towards the normal N1. And at the second interface X dash Y dash, the refracted ray at the interface XY will become incident ray, and the refracted angle R1 will become the incidence angle R1. And at the normal N2, as the light ray QR travels from denser to rarer medium, it will bend away from the normal. That's why the refracted ray RS will move along, the refracted ray will move along RS direction, for which E be the angle of refraction for the interface X dash Y dash. Clear? So if the total slab is absent for the incident ray PQ, so the PQ will move along the same path like this. Let it be P dash. Okay, if the complete slab xy, x dash, y dash is absent, then the incident ray PQ will travel along the same path, that is QP dash. But due to the presence of the glass slab, it bend and travel along RS. That's why the incident ray, which is initially along the direction of PP dash, due to the presence of the glass slab, it will shift and emerged out along RS. So the incident ray will laterally shifted from PP dash to RS. So this, if I am drawing a perpendicular from the emergent ray to the incident ray, so it will become what? This angle, this distance is known as the lateral shift of the incident ray to the emergent ray. RS is known as what? Emergent ray, which is denoted by L. Clear? So now here we can calculate that for the first interface, XY. Okay, for the interface XY, if I am applying the Snell's law, I can write sin I by sin R1, because here the refracted angle is R1, equal to mu, light travels from air to glass. So this implies you can write sin I divided by sin R1 equal to mu of glass divided by mu of air. So this can be written as sin I into mu A equal to sin R1 into mu G. Let it be equation 1. Clear? Similarly, for second interface, x dash, y dash. By applying Snell's law, here I can write sin incident angle will be the R1. So sin R1 divided by the refracted angle will be E. So sin E will be equal to mu. Now light travels for the second interface, glass to air. So this implies I can write sin R1 by sin E equal to mu of air by mu of G, or this implies I can write sin R1 by sin E, or by cross multiplying this I can write mu G sin R1 equal to mu A sin E. Let it be equation 2. Clear? So now from equation 1 and 2, so here equation 1 will be how much? Sin I by sin R1 equal to mu air to glass, so it will be mu G by mu A. So from this we will get mu A sin I equal to mu G sin R1. This is equation 1. So from equation 1 and 2, here mu G sin R1 equal to mu A sin E, and here mu G sin R1 equal to mu A sin I. So from equation 1 and 2 we get what? From equation 1 and 2 we will get, as here mu G sin R1 is equal to mu A sin I, and here mu G sin R1 equal to mu A sin E. So from equation 1 and 2 we will get what? Sin I is equal to sin E. So this implies we get I angle equal to angle E, that is incident angle will be equal to emergent angle. Clear? You have to remember this point as equation 3. Clear? So when a light ray pass through a parallel glass slab through any two parallel interface or any two parallel face, then the light will get laterally shifted, and for this the angle of incidence is equal to angle of emergent, where RS is known as what? Emergent ray. This ray RS is known as emergent ray. Okay, and this PQ is known as what? Incident ray. Clear? Okay, so from this we will get what? Angle I is equal to angle E. So this can be written as the angle of incidence is equal to angle of emergence. So angle of incidence is equal to angle of emergent. Okay, clear? So this is how light get refracted through a glass slab. Now we have to find out what is the value of lateral shift. That means how much amount the emergent ray gets shifted from the initial path of the incident ray. So for lateral shift, of incident ray. So here this L length, the perpendicular distance between the path of the incident ray, that is P dash, and the emergent ray RS, is known as the lateral shift. So how to find out the lateral shift? So now consider the right angle triangle RQ, let this be perpendicular BH T. Okay, so now in the right angle triangle RQT, in right angle triangle RQT, if this angle is I, this angle is R1, this is the normal. Let this X, I am extending the normal N1, which will touch the second interface X dash Y dash at N double dash. Let it be N1. So it touching the normal is extended up to the second interface X dash Y dash, which will intersect at or draw a perpendicular at N dash. Clear? So now in the right angle triangle QRT, this is right angle. Okay, if this angle is R1, this complete angle is I, so this much angle, the angle of deviation, this much angle will be how much? The angle of deviation delta equal to R I minus R, because as light travel from rarer to denser medium, so angle of incidence will be more than angle of refraction. That's why here angle of deviation, this much angle is known as what? I minus R. So in right angle triangle RQT, angle RQT is equal to how much? I minus R. Clear? So this implies sin I minus R will be equal to how much in the right angle triangle? Sin I minus R equal to P by H, which can be written as what is P? P equal to RT divided by what is H? H equal to QR. So this implies I can write sin I minus R equal to what is RT? RT equal to the lateral shift, the value is L divided by QR. So this implies I get the lateral shift L equal to QR into sin I minus R. Let it be R1. Sorry, here this is R is R1. So I minus R1, R1, here it is R1. Clear? So now I let it be equation 1. So now I have to find out the value of QR. What is the value of QR? Now consider another right angle triangle QN dash R. So now in the right angle triangle N dash QR, this angle is R1. Clear? This is the perpendicular and this is the hypotenuse, as this is base. So in right angle triangle N dash QR, cos R will be how much? B by H. So this implies cos R1 will be equal to how much? Here the angle is R1. So cos R1 equal to B by H. B is what? QN dash divided by H is what? QR. So it will be B by H, that is QN dash divided by H is QR. So this implies here cos R1 equal to what is QN dash? QN dash is the thickness of the glass slab, that is already given T divided by QR, and we have to find out the value of QR. So from this we will get QR equal to how much? T by cos R1, or this can be written as T sec R1. Clear? Let it be equation 2. So now using equation 1 and 2. So now using equation 1 in 2 we will get what? Using equation 2 in 1, we will get what? L equal to, in place of QR I can write T sec R1, T sec R1 sin I minus R1. This is the value of what? Lateral shift. Okay. So if a light is incident at an angle of incidence I and it passed through a glass slab of thickness T, then the emergent ray will get laterally shifted from the path of the incident ray by this much, where T is the thickness of the glass slab, R1 is the refracted angle at the point of incidence for the first interface, and I is the angle of incidence. Clear? So you have to remember this formula, lateral shift equal to T sec R1 sin I minus R1. Here R1 is what? The angle of refractive index at the first interface. Clear? Okay, and for this refraction through a glass slab, through any parallel phase, the angle of incidence is must be equal to angle of emergence. Okay. So now we have to study if there are more than one slab or compound slab cases. Okay, refraction through compound slab. So let us consider two slabs which are parallelly attached with each other. Okay, let the thickness of these two slabs be T1 and T2. Okay, and here the refractive index of the surrounding of the two slabs be mu1, and this is the slab having refractive index mu2, and this is the slab having refractive index mu3, and as the surrounding is same, so this also have the refractive index mu1. Clear? And here mu1 is less than mu2 is less than mu3. Okay, clear? So there are two glass slabs having refractive index mu1 and mu2 and surrounded by a medium having refractive index mu1, and the refractive index of two slabs is mu2 and mu3. Clear? And the thickness of the two slabs are T1 and T2. Now we have to consider a incident ray which is travel along this direction. Let the incident ray be P, Q, and this is the normal at the point of incidence. Let it be N1, and here the angle of incidence will be I. So as here mu2 is greater than mu1, so light travels from rarer to denser medium, because mu1 have refractive index less than that of the refractive index of the first glass slab, that is mu2. So here light travel from rarer to denser medium. So after refraction at point Q, it will bend towards the normal and it will goes like this. So let here the angle made by the normal will be R1, the refracted angle. Now I have to draw another normal at the interface which will separate both the slab. Let it be N2. So as this angle is R1, so similarly this angle will be R1. Clear? And now the ray travel from refractive index of the medium of the glass slab having mu2 to mu3. Here mu2 is less than mu3. So again the ray travels from rarer to denser medium. So it will again bend towards what? Normal. So it will move like this. So let it be R2. Clear? And at the last interface, if here I am drawing a normal N3, so this will be also R2, and as here again light travel from mu3 to mu1, that means this is the denser medium and this is the rarer medium, so it will bend away from the normal, it will goes like this, and this is the emergent angle E. Clear? So here there are three refractions takes place. First at the interface, let it be xy. Next at the interface x dash y dash. Next at the interface x double dash y double dash. Clear? So three refractions takes place at the three interfaces, due to which the incident ray PQ moves along QS, then ST, then along TR. Okay. So this is the path of PQ, then it will bend towards the normal N1 and travel along QS, and again for the interface x dash y dash, again light travel from mu2 to mu3. So here the refractive index is less than the refractive index mu3, again light travel from rarer to denser medium, so it will again bend towards the normal N2, and at the final interface x double dash y double dash, the light travel from mu3 medium to mu1 medium, so here it will travel from denser to rarer medium, that's why it will bend away from the normal N3 and travel along TR. Clear? So if I am applying Snell's law at the first interface xy, so for interface xy, applying Snell's law, I can write sin I divided by the refracted angle will be R1 equal to light travels from mu1 to 2. This can be written as how much? Sin I divided by sin R1 equal to mu2 by mu1, or this implies it can write mu1 sin I equal to mu2 sin R1. Clear? Let it be equation 1. Similarly for interface, second interface x dash y dash, at this place this angle is R1, so this angle is also R1, so here the angle of incidence will be R1 for the incident ray QS, and the angle of refraction will be R2. So by applying Snell's law for the interface x dash y dash, I can write sin R1 divided by sin R2 will be the refracted angle equal to, now light travels from mu2 to mu3, so this can be written as sin R1 by sin R2 equal to mu3 by mu2, or this implies you can write mu2 sin R1 equal to mu3 sin R2. Let it be equation 2. Similarly for the third interface x double dash y double dash, we can write what? Here the angle of incidence will be the refracted angle R2, that is R2, and the angle of emergent will be E. So here I can write sin R2 divided by sin E will be equal to mu, now light travel from mu3 to 1, so it will be 3 to 1. So this implies I can write sin R2 divided by sin E equal to mu1 by mu3, and cross multiplying this we will get mu3 sin R2 equal to mu1 sin E. Let it be equation 3. So for the first interface xy we will get mu1 sin I equal to mu2 sin R1, and from the second interface we will get mu2 sin R1 equal to mu3 sin R2, and from the third interface we will get mu3 sin R2 equal to mu1 sin E. So from equation 1, 2 and 3 we will get what? Mu1 sin I is ultimately equal with mu1 sin E. Clear? So again from this we will get what? The angle of incidence equal to angle of emergence, or from this I can write, so from equation 1, that is 1, 2 and 3 I am writing here, from equation 1, 2 and 3 we get what? Mu1 sin I equal to, here mu1 sin I equal to mu2 sin R1, again mu2 sin R1 equal to mu3 sin R2, and again mu3 sin R2 equal to mu1 sin I sin E. So from 1, 2 and 3 we will get what? Sin I equal to sin E. So this implies angle of incidence equal to angle of emergence. Clear? This also valid for the compound slab, and again from this equation if I am multiplying all this equations. So mu 1 2 into mu 2 3 into mu 3 1, it will be how much? Mu 1 to 2 into mu 2 to 3 into mu 3 to 1. It will become how much? 1 to 2, 2 to 3, 3 to 1. So it will become 1. Clear? Because sin I by sin R1 into sin R1 by sin R2 into sin R2 by sin E. So it will become how much? 1, which is equal to sin I by sin E, because I equal to E. So by multiplying these three, we will get what? Mu 1 to 2 into mu 2 to 3 into mu 3 to 1 will gives us 1. So from this I can write, this implies as sin I equal to sin E. So this will multiply and gives us 1. So this implies 1, and mu 1 to 2 into mu 2 to 3 will be 1 by mu 3 to 1. So this implies I can write mu 1 to 2 into mu 2 to 3 equal to mu 1 to 3. Clear? So from this we will get, for the composite slab system, the light travels from first medium to second medium, and second medium to third medium, which ultimately gives us that the light travels from first medium to third medium. That means light travels from initial to final medium. Okay, the in between mediums are independent, or it can be write like this. Clear? So this is how light gets refracted through a compound slab system. Clear? And for this system, what will be the lateral shift? As this is the path of the incident ray, but finally the light will travel along this direction. Let it be like, make it like this. Okay, so this is the lateral shift. Clear? So the lateral shift will be because of slab 1, then due to slab 2. So if there are a large number of slabs, the lateral shift for each slab will get added. So the total lateral shift L net, here the lateral shift L net will be how much? According to the previous formula, here you can write T1 sec R1 sin I minus R1 plus T2 sec R2 sin I minus R2, and so on. As here there are two slabs, so the lateral shift will be this much. If there are more than two slabs, then I can add it, and so on. Clear? So here the lateral shift will be this much: T1 sec R1 sin I minus R1. What is R1? The refracted angle at first interface. T1 is the thickness of first slab, and I is the incidence angle. T2 is the thickness of the second slab, and R2 is the refracted angle, the second interface, and so on. If there is another slab of thickness T3, so the lateral shift will be this much plus T3 sec R3 sin I minus R3, and so on. Clear? So this will be the net lateral shift by using compound slab system. Okay. So this is how light get refracted through a compound glass slab, and how to find out the lateral shift in compound glass slab. Okay. So next we are going to discuss about what is the relation between apparent depth and real depth. So now we have to discuss about real depth and apparent depth. What is this real depth and apparent depth? We all are known when we see a coin which is placed inside a bucket containing water, it seems that the coin is appears some height above its original position. That effect is known as what? Apparent depth. Clear? We already observed that if there is a coin in a container which contains water, and we look from the upside to that coin, then at certain angle the level of the coin is looked some level above of its original position. This is what known as apparent depth. Clear? So if I am considering a case that here is a container which contains a liquid, let it be water or any liquid, okay, any liquid, let it be mu1. Okay, this is the refractive index of the liquid mu1 and the surrounding have refractive index mu2. And here is a coin placed just below the surface and the total depth of this liquid is d, which is the actual depth of this coin. It's a coin. A coin is placed inside this container which carry a liquid of refractive index mu1 and the surrounding has a refractive index mu2, and here is a coin is placed at a depth of d. If someone look just above this, a normal view of this coin will be like this. The ray will come along this direction and this is the interface after which it get refracted, but as the incident ray goes normal, it will goes undeviated and it will go along this direction. Clear? So let the position of the coin will be P and here the point will be Q. Clear? This is the normal incidence, and we have to consider another ray which is go like this, and here I am drawing the normal n dash. So as here this is the angle of incidence I, and here we have to know that mu1 is greater than mu2. That means light travel from denser medium to rarer medium. So as light travels from denser medium to rarer medium, so at this point of incidence, this is the angle of I, and for the normal n dash, the light will travel from denser to rarer. So after this it will get bent and travel along this direction. So I am extending this, so it will strike here. Let this point be Q S. So this is the point of intersection where the light ray will traveling. This will be the Q, this point let be T, and it is travel along this direction R. So the first incident ray which is traveling perpendicularly or normally along PQ goes undeviated, and the second ray which is traveling along PT after refraction, it will move along RTR direction, for which you have extended this refracted ray. It will intersect the normal ray PQ at point S. So this angle here will be how much? R, angle of refraction, and this angle is I. As this is normal, this angle is I, this is also normal, so this angle is also I, and as this angle is R, this angle also R. So let the distance between point Q and T, this distance be X. Okay, these two rays are very close to each other. Clear? So for this condition, in the right angle triangle, now in the right angle triangle PQT, okay, this is right angle triangle PQT, angle Q is equal to 90 degree, okay, PQ equal to the total depth of the water level or the container D. Clear? And let the distance QT be X. Okay. So in this right angle triangle PQT, I can write all the rays are, you have to remember here, all the rays are paraxial. That means angle I, angle R are very small. Clear? And this depth D, and let the refracted ray T R meet at point S, and its distance from the interface, this distance will be D dash. Okay, and the depth D and D dash are measured from the interface of both medium. Clear? So this is the condition you have to remember during this, that all the rays are paraxial, that means they are very close to each other, so angle of incidence and refracted angle at each and every point are very small, and the depth d and d dash are measured from the interface of both the medium. This is medium 2, this is medium 1, so the depth are measured from the interface. So here the actual depth of the object or the coin is d, but as the light ray TR after refraction, if here is a observer, this is the observer's eye, which see when the refracted ray strike its eye, it will see the object at S, which is the image, and the depth of the image is d dash. Here the depth of the image is how much? D dash. Clear? So d dash is the apparent depth. Clear? So now in this triangle, what P, Q and T, as all are the paraxial rays, so by Snell's law I can write what, or from Snell's law I can write sin I by sin R equal to how much? Light travels from 1 to 2, mu 1 to 2, so this implies I can write sin I by sin R equal to mu 2 by mu 1, or this implies I can write mu 1 sin I equal to mu 2 sin R. Let it be equation 1. Clear? But as the rays are paraxial, I and R are very small, so for very small angle sin I can be written as tan I and sin R can be written as tan R. We already know for very small angle sin I can be written as tan I and sin R can be written as tan R, because for very small angle, if this is the right angle triangle, okay, if this angle is theta, this will be P, this is 90 degree, this is S, this is B. If this theta will be very small, what is sin theta? Sin theta equal to P by H, and what is tan theta? Tan theta equal to P by B. Clear? But if theta is very small, if this theta will be very small, then this P value will be very negligible, and then I can write H is nearly equal to B. Clear? If theta is very small like this, if I am considering this is as the hypotenuse, the theta is very small. If the theta is very small, B is nearly equal to H. So if B is nearly equal to H, sin theta will become equal to what? Tan theta. Okay, because B is nearly equal to H for very small angle. If this is the angle which is very small, then this is base, this is height, hypotenuse. So if angle is very small, base is nearly equal to height, so tan theta will become equal to sin theta. So here sin I is nearly equal to tan I and sin R is nearly equal to tan R, as the rays are paraxial. So from this I can write mu 1 tan I, so mu 1 sin I, equation 1 can be written as, so equation 1 can be rewritten as mu 1 tan I equal to mu 2 tan R. So let it be equation 2. Okay, so from triangle sorry PQT and the right angle triangle SQT, because here this is also right angle triangle SQT PQT. What is in triangle PQT? This angle is also I, so tan I equal to how much? P by H. If this angle is I, P will be x and H will be this much. Sorry, tan I will be P by B. So P will be x, B will be D. So this will be x by D. Similarly, from the right angle triangle QST, this right angle triangle, this angle is R, so this angle is also R. This is right angle triangle and this is the triangle I am considering, SQT. So in SQT I can write tan R, this angle is R, tan R equal to again P by B, that is x by D dash. Clear? So from this we will get what? Mu1 tan I, so this will be mu1 x by D equal to mu2 tan R, that is x by D dash. So x will cancel, so D dash by D will be mu2 by mu1. So this is the relation between, what is D dash? D dash is the apparent depth and D is the actual depth, which will mu2 by mu1. What is mu2? Mu2 is the refractive index of the medium to which the light ray is going in, and mu1 is the refractive index of the medium from which lights are coming. So you have to remember that mu2 is the refractive index of the medium into which the light rays are, incident rays are going, and mu1 is the refractive index of the medium in which the light rays are coming from. Clear? And D dash is the apparent depth, D is the actual depth. So here I can write apparent depth divided by actual depth or real depth equal to mu2 by mu1. What is mu2? The refractive index of the medium into which the incident rays are going in, and mu1 is the refractive index of the medium from which the incident are coming from. Clear? So here what is, we have to find out what is the shift of the image. So the shift of the image will be, if this is the actual depth D and this is the apparent depth D dash, so the shift will be, the object is at this place but it will seems to the observer at point S. So this much will be the apparent, this much will be the normal shift, let it be Y. So the normal shift Y will be how much? This height will be how much? D minus D dash. So the normal shift of object is Y equal to how much? D minus D dash, which is equal to actual depth minus apparent depth, which is equal to the normal shift Y equal to D minus, in place of D dash, from this is equal to how much? D dash by D. So from this D dash will be how much? Mu2 by mu1 into D. This relation apparent depth D dash by actual depth D equal to mu2 by mu1. So D dash will be D into mu2 by mu1. So D minus D into mu2 by mu1. So the normal shift Y will be how much? D whole into 1 minus mu2 by mu1. Clear? So this is the expression for normal shift, where D is what? The actual depth, mu2 is the refractive index of the medium to which light rays are going in, and mu1 is the refractive index of the medium from which the light rays are coming from. So this is the expression for what? Normal shift of the object during when light passes from one medium to other medium. Clear? So next we are going to discuss about, so from this you have to remember one thing, that if here is a medium and this is a medium mu1, or it's a rarer medium and it's a denser medium, and this is the interface which separate these two medium, and light rays and the object is placed in the denser medium here. Okay, clear? So if lights are coming from this direction, object is placed in the denser medium and observer in the rarer medium. So here the light rays are going like this. When the observer will see this object, so light rays are going like this. It's denser to rarer. So if I am drawing a normal here, it will move like this away from normal, and as here another ray going like this, so normal it will move like this. So for the observer, the light rays are going like this along this direction, so it will obtain that the observer will see the object at this place. Clear? So if the total depth is d, so and this depth, because both the depths are measured from the interface and this is the complete depth d, so this depth will be how much? If this is d, the apparent depth will decrease, the object, this is object, will observe above the actual depth. So here the shift will be how much, or the depth, this much depth will be d dash. D dash will be how much? If it is travel from here to here, we already described that here d dash equal to d into light travels from mu d to mu r, so mu r by mu d. Clear? So the shift will be how much if r is taken as AR. If the rarer medium is considered as AR, so what will be the apparent depth? D dash. D dash will be d by mu d. Okay, so when light travels from any denser medium to rarer medium which is taken as AR, the apparent depth will be the mu 1 by mu times of the denser medium of the real depth. Clear? You have to remember this, that when observer is in rarer medium or AR medium, when observer is in rarer, that is AR medium, and object is in denser medium, clear? Any denser medium have a refractive index mu. Okay, let it be any denser medium have a refractive index mu. Then the apparent depth is 1 by mu times of the actual depth. Clear? Here the apparent depth is 1 by mu times of the actual depth. Okay, here the object is here, real object. If the object is virtual, this is also happening like this. If light rays are coming like this, so it will be seems like that the object is here. Okay, but when the observer will see, it will move away from this and will be seems like here. Clear? And similarly, when the observer is in rarer denser medium, this is the case when the observer is in rarer medium and object is in denser medium. But if the observer is in denser medium This is mu d where the observer is present, and here mu r which is taken as AR. So now what will happen? Object is here, at a height d. So light rays comes like this, and after refraction it will bend towards the normal and goes like this, and here light comes like this, and after refraction it will bend towards normal, goes like this. So if I am extending this, it will meet here. So the object will be observed at this place O dash. If this is the actual depth d, now the depth, apparent depth will be this much, d dash. So now what will be d dash? See here the apparent depth, d dash will be how much? I can write d dash by d equal to, light travels from rarer to denser, so mu d by 1, because its rarer is taken as AR, so mu d by 1. So this image will get the apparent depth d dash will be mu d into d. Clear? So when observer is in denser medium, object is in rarer medium, the apparent depth will be mu of the denser medium times of the real depth. Here the apparent depth will be 1 by mu of denser times of the real depth. The apparent depth is 1 by mu d times of the actual depth. Here in case 2, if observer is in denser medium, then the apparent depth of the object is mu d times, mu d means what? The refractive index of the denser medium times of the real depth, of the real depth or actual depth. You have to remember this relation, so it will be helpful during solving numericals. Clear? Okay. Next we are going to discuss about total internal reflection, or it is denoted by TIR. So it is a very interesting phenomena. So let consider a interface X and Y which will separate two medium. One is rarer mu r having refractive index mu r, and another one is denser medium having refractive index mu d. And for this case light travels from denser medium to rarer medium. You have to remember, for total internal reflection light have to travel from mu of denser to mu of rarer. This is a important condition for total internal reflection. So what is total internal reflection? So first of all, light travel from denser to rarer medium. So let consider an incident ray, this one, and here is the normal n dash, and here the angle of incidence will be I. So as the light travels from denser to rarer medium, after refraction it will bend away from normal and goes like this. This is the angle of refraction R. Clear? So if I am gradually increasing the value of I, the R will gradually increases. Okay, because if I here, when light travels from denser to rarer, we already know which angle is greater. Angle R is greater than angle I. So as I increases, R will increases. So if I am increasing I, gradually R will increase for a particular angle of incidence. If this is the angle of incidence, for a particular angle of incidence, let the angle of refraction becomes 90 degree, or the ray after refraction goes along the interface, then this angle of incidence is known as critical angle. This is denoted by theta c, which is known as critical angle. Okay, clear? So when light travels from denser to rarer medium, it bends away from the normal, and as I am increasing the angle of incidence, gradually the angle of refraction will get increased, and for a particular value of angle of incidence, the angle of refraction will become how much? 90, or the refracted ray goes along the interface. That particular angle of incidence is known as critical angle. Clear? So you have to remember, when for an angle of incidence the angle of refraction becomes 90, that particular angle of incidence is known as critical angle. Okay, so when light after refraction goes along the interface, for that case the particular angle of incidence is known as critical angle. And if I am increasing the incidence angle more than that of critical angle, like this, the R will further increase. If R will further increase, it will comes back to the same medium. The interface will behave as a reflecting surface, and this phenomena is known as total internal reflection. So when angle of incidence I is greater than critical angle, TIR takes place. The interface behaves as a reflecting surface. Clear? So when angle of incidence is increased further than the critical angle, total internal reflection takes place and the interface behaves as a reflecting surface. Clear? So what is the value of critical angle for any two mediums? So these are the points you have to remember for the total internal reflection. First of all, light have to travel from denser to rarer medium. Clear? Second, for a particular angle, the refracted ray becomes 90 degree, or refracting angle becomes 90 degree, which is known as critical angle. And if the angle of incidence further increases, the interface will behave as a reflecting surface and the light come back to the same medium, which is known as total internal reflection. So what is the value of critical angle for any two given mediums? So as for this case, light travel from mu d to mu r. So I can write by applying Snell's law, sin I is equal to what? Critical angle divided by what is refracted angle, sin. When I is equal to critical angle, the refracted angle will be 90 degree, sin 90, equal to light travels from mu d to mu r. So this implies I can write sin theta c by sin 90 is how much? 1, equal to mu r by mu d. So this implies I can write the value of critical angle theta c will be sin inverse mu of rarer medium divided by mu of denser medium. You have to remember this. This is the expression for critical angle for any two given medium when light travels from denser to rarer medium. Clear? So when incident angle is equal to theta c, the angle of refraction will be 90 degree. So if I am incidentating an angle ray which is traveling from rarer to denser medium at an angle of 90, it will goes to the denser medium at an angle of theta c. The reverse will also takes place. Clear? So for an example, if here is a medium, this is having refractive index √2 and this is having refractive index 1. Let it be mu r equal to 1 and mu denser equal to 2, and light travels from rarer to denser medium like this. So find the value of theta c for these two interface, mu r of 1 and mu d of 2. Let this is the example. So from this I can write what is sin theta c equal to how much, mu r by mu d. So this implies sin theta c equal to mu r is how much, 1 divided by mu d is how much, √2. So this implies theta c equal to sin inverse 1 by √2, which is equal to 45 degree. So for this particular case, the theta c value will be 45. Then it will, the refracted ray will goes like this. If the angle of incidence increases further, it will be 45.00 up to very large number of decimal place, then 1. Then it will takes total internal reflection and the reflected ray goes back to the same medium. So at that verge, when the angle of incidence increases just further the critical angle, total internal reflection takes place and the interface behaves as a reflecting surface. So this phenomenon is known as what? Total internal reflection. Clear? And important points regarding the total internal reflection, you have to remember that light must travel from denser to rarer medium, and for total internal reflection the angle of incidence must be more than that of the critical angle for the two linked mediums. And how to find out the critical angle for any two medium, you know already. So now we have to discuss about some application of total internal reflection. So application of TIR. So what are the application of TIR? First, the application of TIR is how a diamond shine. When generally diamond gets caught like this. So when light enter into this at any angle, if the light incidence from the surface of the diamond, due to which if the critical angle, the angle of incidence will be more than that of the critical angle for the air and diamond interface, then the light will completely get trapped within it and it will move like this. Clear? Then the light will remain inside the diamond and the diamond will dazzle. That's the cause when a diamond is placed in a dark room, it glazes or it shines, because the light which is incident on the diamond, it will trapped within it due to total internal reflection. And for diamond air case, the critical angle value is nearly equal to 24 degree. So if the light which is incident on the interface of the diamond and air, if that is more than that of 24 degree, the light will completely trap within the diamond, due to which the diamond will shines in dark. Clear? Similarly, when a air bubble is placed in a liquid, it is also shines, because in air bubble which is placed within a liquid or water, if this is water having refractive mu g and within it there is a air bubble, so within it this is air. So we already know air is denser medium and water is air is rarer medium, water is denser medium. So when light enters from the air medium, from the water medium to the air medium, so it goes from the denser to rarer medium. So if the light incident on the air bubble surface at an angle which is greater than that of the critical angle, which is nearly equal to 49 degree, then the light will trapped within the air bubble and it will start shining. Clear? So when any incident ray incident on a interface more than that of the critical angle, and provided that the light travels from the denser to rarer medium, the light will completely trapped within it due to total internal reflection. That's why when light travels from the water medium to air medium in a air bubble which is inside the water medium, it will glaze, or it will shines if the angle of incidence of the light will be more than that of the critical angle, which is nearly about 49 degree. Clear? Similarly, by the application of TIR, we are using total reflecting prism. So what is total reflecting prism? So total reflecting prism is a right angle isoscale prism like this. If this is a isoscale right angle prism, this will be 90 degree and these two angles are 45 degree. Clear? Isoscale prism. So if light incident from this direction, here is a object, it will be A and B, line incident from this direction normally, and it will strike at this interface, let it P, Q, S, at the interface PQ. If this angle is 45, this is 90, and if this angle is 45, so if the incidence angle will be more than that of, because here the critical angle is for the glass and air phase will be 42 degree, theta is equal to 42 degree. So as here incidence angle will be 45, so it will be more than that of the critical angle, so it will deviated along same direction and pass like this, and at this same interface it will again incident at an angle more than that of the critical angle, because for glass air interface the critical angle is 42 and here the angle of incidence will be 45, so it will again get deviated and return back to the same medium. As here it is acts normally, it will go on deviated like this, and this will be the point A. Similarly from point B, if this is the point B, another ray goes along this direction, it will strike here, and here is a normal, it will goes like this, and here is a normal, it will again comes like this. So this will be point B. So as here the object is along this direction, after total internal refraction the object gets inverted, and during this process there is no loss in intensity, because the complete ray get deviated without any reflection and refraction, without any refraction. That's why there will be no loss in the intensity. So we are getting the image as same as that of object but in inverted position. This also can be used as a the total reflecting prism can also be used like this. This angle is 45, this angle is 45, this is 90. If the light rays are coming along this direction, normal to this, and it will strike at the interface P, Q with an angle which is greater than the critical angle 42. So it will again deviate along this direction and travel along this direction. Clear? So the total reflecting prism is used in periscope and also in prism binoculars. Clear? To get the image of same intensity as that of object without any loss in the intensity. So these are some applications of total internal reflection, and also in day-to-day life we are using optical fiber, which is based upon the application of total internal reflection, and the mirrors that we saw in summer days. This is also the cause of total internal reflection. So today we already discussed about how refraction takes place through a glass slab, what is the apparent depth, what are the lateral shift in glass slab, and what is total internal reflection and what are its application. In next class we will discuss further. Okay, thank you.